Last class, I had you guys do that simulation for applied forces and static friction and kinetic friction. So you looked at that, you got a chance to see and get an idea of it. Now let's actually get into the nitty-gritty here. So we're going to look at 4.6 and 4.7 together. 4.6 and 4.7 really get into free body diagrams, motion, forces, but then in 4.8 we're going to look at friction. So for the next section for today and probably part of Thursday's class, we're going to look at this section, but it's really nothing to do with friction yet. So I don't want you to jump the gun on the lab. Hold on to the lab still in case you want to go back and edit anything to do with friction, but we're not going to get to that until 4.8. So that won't be due for a little while. So the main things we're going to look at, free body diagrams, we're going to look at equilibrium problems, we're going to talk about weight versus mass and how they differ. We'll talk about what's called the normal force, and then tension. Tension is the last thing we're going to end on with this lesson. So let's start right away. So first, a free body diagram. A free body diagram is a diagram showing forces acting on an object. Acting on an object. So, the diagram on the left is not a free body diagram. The diagram on the left is called a force diagram. A force diagram shows all forces acting for an entire problem. So there might be a problem where, how many people have played billiards or pool before, right? Okay. So you're playing pool and you have a combo shot. So you're hitting the cue ball, and say you have to hit the cue ball into a solid, which is what you are shooting for, which then hits a strike, which then hits a solid, right? You don't want to scratch hit the wrong ball first. So you have a combo shot. And during that combo shot, there are a lot of interactions. The cue ball hits the first ball hits the second ball, which is like the transfer one, and then the second one hits the third one, which is what your target ball actually is. During that process, there are forces acting on all of those billiards balls. All four of them have forces acting on them. The first one is what you strike it with to start. It starts to move, it hits the first billiards ball. It gets rebounded slightly. The first billiards ball hits the next one, which hits the next one. It involves like a chain reaction. So when we look at these diagrams, if I looked at all of the billiards balls at once, I would be looking at what's called a force diagram. But if I specifically said, let's focus on the cue ball, for example, and we only look at the cue ball. So the cue ball would only have an applied force to start, some slight friction, very little because it's rolling. Then when it hits the first ball it's supposed to hit, it would have an applied force backwards or against its motion. So when we look at a free body diagram, we're looking at the diagram shown here on the right. This is the free body diagram of the car itself. So on the left, we see the car and we see the wall. We see both of those things. But on the right, we see only the car. Yeah.
You said that, you mentioned it briefly, just that if something is rolling, it doesn't have as much friction. So why does a car have so much friction?
Well, that's different. So a car that rolls on tires, if you don't hit the brakes and you just let the car coast, it'll coast for a while. Eventually, stop it. It will come to rest because there's internal friction in the axle, in the engine, with the pistons. There's a lot of frictional losses. But when something rolls traditionally, it exhibits much less sliding friction. So when I take an object and slide it across like that, that exhibits what's called kinetic or sliding friction. But if it were one of those carts that we've looked at and I did the same thing, it would not stop as easily because it's rolling. So when an object is rolling, its kinetic friction or its sliding friction is very, very, very low. Almost zero. It's really the friction that's lost in the axle and the turning of the wheel. Now, rolling friction is a whole other topic, and we'll get to rolling friction. And that provides some propulsion forward. Like when you walk, right? When you physically walk, you're pushing. You're literally pushing every time, whether you realize it or not. A car tire is doing the same thing. When a car tire starts to roll, the rubber in the tire grips the ground, and it pushes off the ground each time. So as a car tire rolls very slowly, if you want to think about it, every time it's in contact with the ground, there's friction pushing back against the ground, which is propelling the car forward. Okay, so there's a lot more friction in sliding and rolling than you think. Okay? Now, for this example here, this car on the right is the object of interest. So the way we're going to draw things in this class is with a dot showing the center of mass of the object, and then we're going to draw all of our forces acting from that dot. So the force acting to the left is a force on the object. Well, I might call it F in this case. I'm going to call it FW for wall. the force from the wall acting against the car when it hits the wall. Then here we have the force due to its weight, which is called gravity. And we're going to get into that in a moment. We're going to get into all these types of forces, I promise. And then what we have is the floor pushing back up. The floor pushing back up. And we're going to call that normal force, and we'll talk about that in a moment as well. But just to give you an idea of what this diagram is really indicating, when you're sitting in your chair, why aren't you just falling down to the ground? Because your chair is supplying a reaction to your body's desire to want to fall. You're in a gravitational field right now. So if I were to literally just pick up this case and drop it, it falls. But if I had my hand beneath it and I drop it, it doesn't move. Because my hand is supplying some sort of a reaction to keep it there. I have to apply an upward force, and that upward force comes from the tension in the muscles in your arm. So the tension in the muscles in your arm translates to your hand. The muscles, ligaments, and tendons, all that stuff in your hand are what are keeping this in place. Well, when a chair pushes back against you, we simplify it. We call it a normal force. A normal force, meaning a reaction. And we'll get into normal force a little bit, but those are the three forces that are acting on this car. The wall, which is stopping its horizontal motion. Gravity, which is pulling it down. And the floor, which is pushing back up. Now, technically speaking, if we look at the floor here, that should not be locked, sorry. When we look at the floor here, the floor is actually in contact with the car in 4 different locations. Each tire. Every tire is a different placement or a different amount of force being distributed. So each tire is technically carrying a quarter of the weight of the car. Think about your feet, right? Why is it so much tougher to stand on one foot?
All of your weight is on one foot.
Versus
Balance between two.
Yeah. With 2 feet, you can balance. You can balance left to right. You can balance kind of forward and back, not as much. You notice that on the subway? Everybody notice that on the subway, right?
Yeah.
If your only direction is balanced one way, you're going to fall. So you need to either be leaning against the door, which everybody loves that spot on the subway, right? Because you can't move left to right because your feet are there. You're pushing back with friction. The door's pushing you back. You're stable. Or you need to be, if the train is moving this way, your feet need to be this way, and you have to be holding a pole like this. The pole prevents you from moving left to right. The feet prevent you from moving front to back. So when we talk about stability here, this car specifically has 4 stability points. The tires each take on a quarter of the weight of the object. This is the object's weight right here. Okay, so let's get into the definitions and other stuff. We're going to actually do this. So start with the phrase equilibrium, which we've talked about already. Equilibrium is a balance. In chemistry, you talked about temperature equilibrium. And simply put, when the temperature of 2 substances that are separate are the same temperature. They reach what's called temperature equilibrium, or thermal, to be more specific, thermal equilibrium. And when does this happen? You drop an ice cube into a cup of water, eventually what happens to that ice cube? It melts. And the cup of water eventually is 1 overall temperature. Whereas initially, the ice was a very cold temperature, or low temperature. So it was absorbing the heat, and then the hotter substance that it was in was actually giving its heat to the ice. That's a whole other idea of exothermic and endothermic processes. But the idea behind it is that they eventually reach thermal equilibrium, which is when the temperature of the fluid, or liquid in this case, and the temperature of the ice cube eventually match up. In this course, we're going to specifically, in mechanics I should say, in mechanics, because we'll get into thermal stuff maybe later in the year. In mechanics, we're going to talk about force equilibrium. Force equilibrium is seen all the time. You're seeing it right now. You're exhibiting it right now. Again, your weight wants you to fall to the ground, but why aren't you again? What's holding you there? Physically, what's holding you there? Not the force, but physically, what is it? The chair. So the chair pushing up balances your weight pushing down. So we would say you're in a state of vertical equilibrium. Vertical, right? We need to know the definition of vertical and horizontal, as we keep saying. You're in a state of vertical equilibrium. Now, horizontally, you're also in a state of equilibrium, but unless you physically push yourself left to right, there's no forces at all acting on you horizontally right now. But there's always always a vertical force acting on you, I should say, if you're on a planet, or if you're within the gravitational pull of a planet. If you're just out in outer space, there is nothing pulling you toward the ground or toward the surface, except the closest planet nearby, and that gets into like how close are you to the planet, if gravity affects you or not. But on Earth, on a planet, the idea is that you are always feeling your weight pulling down on you. There's always a vertical force acting on a body, and that is that force called weight. Well, normal force pushes back, that's what equilibrium is. What's an example of equilibrium outside of what we just gave here? What's an easy example you can think of equilibrium? Yeah?
Economics, I guess, like on a graph.
What you're talking about, like what?
Like the money you invest, the profit you make, and then the equilibrium to see where it is.
Yeah, that's a great idea. That's a great example. When you think about what's called the break-even point, okay? When you think about when your revenue eventually exceeds your cost, you have a portion, it's called a profit margin for that reason. There's a margin of a gap each time, and eventually they equate. That would be considered equilibrium. Good example, yeah.
Parked car.
Say again?
A parked car.
A parked car is in equilibrium in several ways. What if it's parked at an angle, Maura? And how do you keep it in equilibrium?
The brakes are pushing back in the other direction.
Yeah, you put on the emergency brake usually when you're parked at an angle, because there is a chance the car could start to slide, and the e-brake is a stronger brake applied to your car wheels. What else?
When you finish a bungee jumping, you just dangling at the bottom.
Yeah, that's a great example. During the bungee jump, a lot of forces are acting on you, right? But eventually what happens? You eventually just settle out, you're hanging there, right? So your weight pulling down is balanced by the spring force pulling up. A bungee is a spring. Think about a spring, right? Like a slinky, a spring. A bungee is just a spring. So we're going to talk about Hooke's law, which is spring forces later. So yes, the spring force pulling up would be balancing the weight pulling down. There are infinitely many examples. I'm just trying to get you guys thinking outside the box as to where you could see equilibrium. The simplest one that a lot of students like to think of is a tug of war. When a tug of war is in a stalemate, think about what is that called? Color wars, right? You know what I mean? When you have a tug of war, if you're physically not moving, it means that the force applied in both directions is the same. They're balanced. Okay? They're balanced with each other. Let's keep going. We talked already about action-reaction pairs, but let me again just reiterate. This is Newton's third. Newton's third law told us about the concept that for every action there's an equal and opposite reaction. So I gave the example of a person jumping on the earth. Right? Do you remember the example I gave? I said how you kind of move the earth because there's a force acting up on the earth. Let me give another example for this. So the other example I like to go through is thinking about a hammer with a nail. So let's start by drawing, for now, I'm just going to draw, God bless you. I'm going to draw a surface. Those lines mean that to the right of this is a solid surface. You'll see this a lot in physics. Okay, those slash lines like that. I could also draw it like this, which means that that's a ceiling up top. Okay, that just means it's a surface that you can't get through. So let's say I'm going to blow up this image a lot. I'm going to blow it up. So let's say this is our nail here. That'd be a huge nail. I mean, I guess relative to the surface, we don't know, but the hammer would be enormous then, right? So the hammerhead would be bigger than the nail. So if I were to draw the hammer that's actually hitting this nail, the hammerhead would be like, and it's got that claw on the end of it, and that would be like the hammer like that. Not bad, actually, my art skills. It looks like a mallet more than a hammer. So you're hitting on this nail, right, with a hammer. So if I were to think about this, and I were to use Newton's third law, I'd say, well, for every action, there's an equal and opposite reaction. So when I hit the nail with the hammer, the nail hits me back with the same force on the hammer itself. So we know that when this hammer strikes the nail, if I were to draw the hammer here, on the right I'm going to draw free body diagrams, and the nail over here. Let's take a look at our free body diagram for both of these. So first, the nail physically feels a force from the hammer that's acting on the nail itself. It's physically acting on the nail. That force is directing it into the wall. So this is a force. I'm going to say just FH for now, the force of the hammer. I don't want to get into too much nitty-gritty substance, just the force of the hammer. Okay. Now, that same force applied by the hammer on the nail comes back against the hammer itself. and that's the force from the nail. So those are my pairs right there. That's my pair right there. That's my pair of balanced forces, my action-reaction. Again, the hammer applies a force to the nail to the right. The nail responds by applying a force on the hammer to the left. But here's the thing. If I were to then draw the rest of the forces acting, I could see, why does this nail accelerate? Because the wall pushes back against the nail, but with very little force. The wall can't withstand the force of the hammer acting on the nail. So therefore, the nail penetrates the surface of the wall and embeds itself. So this is because FH is greater than FW. The hammer hitting the nail is stronger than the wall hitting back on the nail. Sure, the nail still hits the hammer back with the same force it applied. FH is equal in magnitude to Fn. They're the same thing. If FH is 10 newtons, Fn, feeling the pushback, is 10 newtons. If you've ever fired either a regular gun or a BB gun, or even something like a water gun, like a super soaker or a Nerf gun, there's recoil for all things. Anybody know the term recoil? Does that ring a bell? Recoil? How would you describe? Show me physically what recoil would look like. What would it look like? Show me. Right? This is what you see when you think of recoil. Recoil is the concept that the gun is propelling the bullet forward. So the bullet wants to propel, the gun is propelling the bullet forward, so the bullet wants to propel the gun backward. That's the action-reaction pair. So you feel this recoil, this force backward on you, just like the hammer. If you've hammered before, you know this, and this is like an unfortunate thing. People have accidentally hurt themselves at times. If you hammer, and you hammer hard enough, the hammer's going to rebound off the nail sometimes. Because again, the nail is pushing back on the hammer. And if you hammer hard enough, it can rebound and hit yourself physically, like in the face. So that's why when you hammer, you never hammer with your face, like you never hammer like this. Because if it rebounds, you're going to smack yourself in the face with it. So when you hammer on the side, and then your location on the hammer changes based on torque, which we'll talk about a little bit later in the year.
The play last year, I took the recoil too early and the sound effect didn't come in. And I was like, oh.
And you were like this, and then the sound effect?
Yeah, I was like, darn it.
But the recoil, you have to act it out because you know what would happen in physics.
Then they told me to not do the recoil because then the cue would be wrong.
Timing for it?
Okay.
So in this case, the hammer, why isn't the hammer going to actually propel you and hit you back in the face? Because you are holding it. You are an applied force. So if your applied force in green here can balance, I'm going to say FP for a push. If the push you give it after it hits the nail can balance the recoil that it has, it's not going to recoil against you. So again, Fn and FH are the action-reaction pairs here. That's the action-reaction pair. Everything else going on in this arrangement has to do with external things. The wall, that's an external thing. That's a force applied against you. You holding it, you hitting, and physically after the hammer strikes the nail, you preventing it from doing this, like by physically holding it, that's FP. FW and FP are these external forces outside of the action-reaction pair. But FH and Fn are equal and opposite to each other. Guaranteed, they have to be. Their values are the same, but they're in opposite directions. That's the whole concept of Newton's third law.
Is there a vertical arrow on this?
On this diagram, we could technically say that, but that's not of interest right now. But yes, theoretically, the weight of the hammer acts down, so you would have to apply a force upward also. So there would be Fg pulling down, and Fp2 instead of Fp1, another applied force, you vertically holding it upward. Same thing with the nail technically, you have to hold it there with your fingers, right, beforehand? So gravity pulls down, but this, you holding it there is technically applying force upward to balance it. I'm not drawing it though just because we're not interested. Yep. Or just because it's not that it's small, it's just that Jack right now, that's not the focus of the problem. So I'm not drawing them here. Because I'm not, yeah, exactly. To discuss what I want to discuss, I didn't need the y direction, so I'm not drawing for that reason. But for any other free body diagram this year, we draw all forces acting on it for any given scenario. This is just a different, this is like an example where you might see it as well.
So on the Earth, is there ever an example where there's like no external forces?
Where there's no external forces?
Yeah, because isn't there always going to be some minute external force?
It's a great question, George. What do you think? where there would be no external forces. I mean, gravity acts on all objects, so technically speaking, there's always gravity. So no, there would never be a situation where there's no external. Could the external forces balance each other? Sure. Gravity balanced by the spring force of the bungee. That's a balanced equilibrium. But technically, those are both external forces. If the net overall external force is zero, though, that's where equilibrium comes into play. But yes, technically speaking, everything has an external force acting on it. Everything. Even objects that are at rest. Valentina.
Do force of the hammer and force of the wall have an action-reaction pair, or you said
No. So, again, the force of, you're talking about these two right here?
Yeah.
Yeah, those do not have a third force as a pair. So, the wall, okay, let's think about this for a second. The wall is providing this response because it's a rigid member. It's not, let me think for a second. The wall itself is not an action. The wall itself pushing back would not be considered an action. So, it's a great question, right? Remember the paragraph for that one. Because Newton's third law says all
Yeah, that's
in pairs, yeah. I guess technically if we drew a free body diagram of the wall, the nail acting on the wall and the wall acting back on the nail, but that wouldn't be balanced either.
The nails.
And what about the person itself? Alright, so actually here, technically speaking, this is getting into really nitty-gritty now, but if I strike a hammer into the wall, the hammer pushes back against me, my hand holds it, with my hand to hold it, I also have to have some grip on the ground, so there's friction that's there as well. So the other balance of FP would probably be friction between the shoes and the floor. And then the balance of FW pushing forward would be the structure backward.
Does that like vary based on how hard you push the nail into the wall?
Sure, absolutely. If you swing, if your push is harder after the collision occurs, yeah, then it would vary the amount. It would also vary the acceleration with which the hammer pops back towards your face. Yeah, it's an interesting question. Let me think about that further, because I'm wondering, like, yes, all things have a pair, but does it matter? It doesn't matter in this case because we're not looking at the wall. We're looking at the nail and the hammer. But had we looked at a free body diagram of the wall and a free body diagram of me as a person, for me, you'd see the friction, and for the wall, you would see some sort of a reaction from the wall being embedded into the ground. But then we get into the whole, then what is the wall connected to? The earth. The earth is the major body. So like you could continue this further and further out to every single thing that's connected. Like me pushing against here is now the floor stuck to the ground. The ground is now stuck to the earth. So in the end, it goes back to everything is technically connected to the earth in a sense. Does that kind of make sense there? But yeah, we'd have to do like 3 or 4 more free body diagrams to see all the other pairs of forces there. It's a great question, Valentina. One I was not thinking of at all. All right, so let's take a look at weight. Let's take a look at weight. And weight is a little bit different than mass. And here's what I need you to recognize. Weight is a function of gravity. Weight is a function of gravity. Remember, mass, we talked about the simple definition of mass. The simple definition is the amount of matter that makes up an object. Well, that's never going to change unless you physically lose or gain mass by exercising or by consuming food. Those are the 2 ways that you can lose or gain mass physically, right? You eat a burger, you gain mass. You exercise for an hour and a half or run around or whatever, or walk up and down Loyola flights, right? Enough times, you lose a couple calories. You try to at least. But the idea behind it, right, behind losing or gaining mass is by changing energy. This goes to Einstein. Einstein said, well, energy is really just mass. So by intaking a bunch of mass, you're intaking calories. That's why you have calories in the back of the label, which are a measurement of energy. So you literally are consuming more and more caloric intake and therefore gaining mass. But when you expend energy and you use energy to physically run, you are therefore losing that energy in the form of mass. So mass can be lost and gained only due to losing or gaining some sort of mass, whether it's an intake or an outtake, or an output, I should say. Weight, though, is very different. Weight is a function of your location more than a function of your object. So if I were to go to the moon, and I've discussed this with you guys already, the gravitational constant on the moon is about 1/6 of the Earth. So if I were to go to the moon, I would feel like I weigh 1/6 of my actual weight, because little g on the moon is only like 1.6. Okay, lowercase g is only around 1.6 on the moon, whereas on Earth it's around 9.8. So when we talk about weight of an object, the weight that you feel is a result of the gravitational field that you are immersed in. So if you change the gravitational field, you change your weight. Gravitational fields actually change not just from planet to planet, but based on elevation as well. Not significantly enough, but enough that if you were a real engineer or scientist, you would account for it. Meaning, if you're at the top of a mountain versus 2 or 3 miles below the Earth's surface, gravity is different in those two spots. As you get further from the center of the Earth, gravity weakens, actually. 9.8 becomes 9.79, 9.78. It gets lower and lower as you elevate further away. If you are closer to the center of the Earth, gravity is stronger toward the center of the Earth, which is why a lot of the planet's material is more dense as you get closer to the center, because it's got more of a pull toward it. Yes?
How do we figure out that gravity is 1/6?
Oh, that's a great question, actually. I don't know the original experiment, but I know that when we did set foot on the moon, data was absolutely taken. So you could drop an object in time of free fall and calculate it.
Yeah.
Right? Y equals y0 plus v0 t plus 1 of at squared. V0, y0, those things drop off. You physically have the height it falls, and you can time it. But I don't know, actually. It's a great question. Where was the first calculation of moon's gravity? I don't know.
But is there air resistance?
Does the moon have an atmosphere at all? Anyone know?
Sure.
I don't think the moon has an atmosphere.
No,
Okay.
I don't think so.
So I'm going to guess that there is no air resistance. Yeah.
Yeah.
But it does have gravity. So even if you jump and push off, you're going to get pulled back.
Yeah.
You know what I'm saying?
Yeah.
It's not like you could just jump and you would go forever in space. There's no air resistance. Gravity.
So the kinematic equations that are like ideal on Earth are like actually what goes on.
What do you mean?
So like the kinematic equations do like the air resistance.
Oh yeah, they'd be perfect for the moon. Yeah, actually, absolutely right. Yep. Very true.
We're like that would work.
So again, remember that your mass doesn't change, only your weight, right? Your mass doesn't change, only your weight. Let's look at a first example. All right, so our mass is 25 kilos. What is the magnitude of its weight on Earth? This is a quick plug and chug. What about on Jupiter, where the acceleration due to gravity is around 2.64 times that of Earth? So I'm going to go through this quickly because it's a plug and chug. So I've got mass given first as 25 kilograms. How do I know that's mass? Besides, it says an object's mass. I get that. But how do I know? Juliet? Good. The units. What would the units be if it were the object's weight? What would it be? In English system, it would be pounds, yes. But in SI units, what is weight measured in? Newtons. So let's jot that down if anything comes. Remember last class we talked about newtons as the unit of force? So if I talk about my weight, or if a problem says an object of 20 newtons, it's referring to the object's weight. If it says an object of 20 kilograms, it's referring to its mass. Absolutely changes your results of any problem if you mix them up. So really important that we get that weight is units of newtons and mass is units of kilograms. It's got to be memorized. Okay, you got to have that up here. It's one of the few units, by the way, mass, that has a prefix to it. Almost all of the units have no prefix. Right? Seconds is just seconds, not milliseconds, not megaseconds. Newtons are just newtons, not kilonewtons, just newtons. But the base unit for mass in physics is the kilogram. Kilogram is the base unit of mass. It's not like, oh, kilograms, so that's 1,000 grams. So when I see 25 kilograms, I should write 25,000 grams. This is one of the few times that you do have a prefix in the base unit. You follow what I'm getting at right now. You do not need to adjust this into grams. I know in chemistry a lot of the time things were in grams, right? Because you're measuring small things, and everything else was rated to grams. In physics, everything is really made to kilograms. Now, I shouldn't say everything. If you look at like quantum mechanics later on, you'll get into much smaller objects, and then you'll be talking about, remember AMUs, atomic mass units? stuff like that, you can use instead of grams or kilograms. But for macro physics, on a big scale, it is kilograms. Now, we are asked to find the magnitude of the weight. The magnitude of the weight. So we're looking for this, but we're really looking for this. Okay, it's magnitude. Magnitude simply means its value, again, without the direction included. Its value without the direction included. So if I'm looking for weight, I start by saying, okay, weight equals mass times gravity. So if I get weight in general, the mass of this object is 25 kilograms, and gravity is 9.8 meters per second squared. Okay, this is absolute value I'm looking at here. It doesn't really matter because I'm looking at a positive quantity here. When we get into free body diagrams and we look at direction in those, then the sign of negative or positive will matter. But for now, it doesn't matter. And I've been using 9.8. Sorry, not 9.81. So I'll get rid of the 1 there. So that'll give me the weight of this object on Earth. What does that come out to be as a number here? Yeah, give me a quick number so I don't have to wait. Thank you. 245? Even?
Yeah.
Thank you. Okay, so that's the weight of the object on the Earth. Which way does weight act again? Down. It acts down. So when we get into equations of motion, we're going to call weight usually a negative force. Sometimes we'll call down positive instead of negative, actually. And we'll talk about when that is. Pulley systems and stuff. Really help you a lot for AP Physics. If we get covering that now this year instead of next year, which I've been having to do a lot of in AP, I think we cover it this year, and it makes it a lot easier for next year. So we'll talk about when down is positive, and that's a weird scenario, but we'll get to that, I promise. So for now, because we're looking at the magnitude only, we're looking at only a positive value. Now, I go to Jupiter. How do things suddenly change? I can do two things. I can do it one way or another way. Give me a suggestion of how to approach this. Give me one way.
Can you multiply 9.8 times 2.64 times 25?
Yeah, so just pretty much change your gravitational constant by multiplying it by 2.64. Would everybody agree with that? So what's the quicker way to do it, though, to get a quicker answer, Jack?
Multiply 2.5 by 2.64.
Yeah, because technically, see, I kind of set you up there. Sorry, Caroline. It was one of those scenarios that you knew that was going to be an easier answer. So I could do this. I can multiply by 2.64, right, to now give me Jupiter. And inherently, what am I doing? I'm just taking this 2.64 and carrying it down. So I would multiply by 2.64 here, and then we can get the weight on Jupiter. Okay, so the weight on Jupiter is Earth's weight times 2.64. Okay, that'll turn out to be 646.8. I'm just doing it quickly. I have it written down here. Okay, and those are measured in newtons. So on Jupiter, 646.8. On the Earth, we're looking at 245. Clearly larger on Jupiter. Why? Jupiter is more
Dense.
Oh,
what is it?
it's more mass.
More, you're on the right track.
Wait.
Massive. It is, we need vocabulary, right? It is more massive. Jupiter is more massive. So Earth's weight is here, then we multiply by this number, and we get Jupiter's weight over here. Jupiter is more massive, it has a higher gravitational pull. You would feel like you weigh more on Jupiter. Jack?
If you're hypothetically 646 pounds,
Whatever, yeah.
on Jupiter, what would happen? Like,
Okay, let's talk. I was about to follow up. So, before I answer Jack's question, I'm going to pose a question for you. Here's my first question is, has anybody ever seen, there's a show called Dragon Ball Z? I maybe referenced this at any point. Come on, be honest. Anyone ever seen it? Somebody in the class has got it.
Hang on.
Okay. Goku, have you heard the name Goku before? Yeah. Guy's got yellow hair, it's all sticking up, right? Okay.
Yeah.
So I'm going to give you a little background on Dragon Ball Z. I love Dragon Ball Z. It's my favorite show ever. It's really good. It really is. So, anyway, one part of the show, there are these characters in the show. It's all about like saving the universe and these fighters and stuff. And they're training in the show, okay? And the main character, his name is Goku. He's training. He's trying to train so that he can fight against this like, evil lord called Frieza. And it's early on, this segment in the beginning of the very beginning of the show that happens. So if you watch like the first like 30 episodes, which are only like 20 minutes each, you'll cover what I'm talking about. Somewhere. So Goku is training, right? And here's here's what Goku's a really smart guy, also, good fighter but smart. So he realizes, you know what? If I could go to the planet and fight this evil lord on his planet, or wherever it is he's going to fight in, but train on a planet that has a much higher gravity, when I get to the new planet, everything will feel lighter to me. Think about it, right? So if I go to the moon today, if I walk to the moon, if I launch to the moon, and I pick up this marker on the moon, if this only weighs a half a pound, now it only weighs, what is that, a 12th of a pound. It's 6 times less weight on the moon than it is on the earth. So if I were to pick up, let's say, all right, for lifting weights, right? Dumbbell sizes. You look at pictures of Goku right now?
Yeah, I was seeing that.
Yeah. So you're lifting, say you're lifting a 15-pound dumbbell, and you go to the moon and you lift the same dumbbell, it's only going to feel like it weighs 2.5 pounds. It's going to feel like it's a sixth of its weight. So you as a person would suddenly feel a lot stronger. So in the show, Goku has somebody create a ship for him. By the way, they can travel at the speed of light. Like, a lot of physics is not true in the show, but this part is really cool. And the ship can simulate gravity. And what he does is, every day, he increases gravity by another G. So on day 1, it's 9.8. On day 2, it's 19.6. On day 3, it's 27, whatever it is. And he trains for like 1,000 days. And he also uses his time dilation, so he can train for 1,000 days, when in reality, it only is like 4 days that have actually gone by. That's called time dilation with speed of light. Anyway, so Goku trains until he gets to 1,000 times gravity, and then when he gets onto this planet, he like steps off the ship, and like a normal jump, which would be like this, he jumps 1,000 times higher suddenly. So he's this like super strong guy, which is really where the whole premise of the show starts, where he becomes like what's called a Super Saiyan, which is another level of strength. Anyway, my point is, what would happen, Jack, is exactly that. If you went to Jupiter, you'd feel weak, because Jupiter has a stronger gravity than Earth. But if you went to the moon, you'd feel strong, because gravity on the moon is less than the Earth. So it's relative to where you train. That makes sense? Long answer,
I
but
think I've seen something like this on Sesame Street.
it's on like Cartoon Network and stuff.
Like Grover was like trying to pick up a shot and he was like, oh, why?
Since your weight,
Let's listen.
since you are like 1/6 as well, are you able like to harness your energy because you're lighter as well?
So you're lighter, but your muscles are still exhibiting the same strength they had. So remember, what causes you to jump and walk are your muscles. So it's not the mass of your body or your weight at all. It's your muscles themselves. So when you jump, because you feel like you weigh less, your muscles are now lifting with the same force, but 1/6 of the weight. So you're going to go 6 times as far, or 6 times as high, or 6 times as fast, or whatever it may be for that
Further
time.
faster.
Okay?
What is it?
Jack.
For those like airplanes that like go 0G, how do they do that?
For airplanes, and when people like float and stuff,
Yeah.
they just do a free fall at the exact same rate of gravity. They free fall at 9.8 exactly. So that when they're falling, people suddenly feel weightless in there. We'll get into more of that when we get to like gravitational constants and gravitational motion of planets. Oh yeah, that's exactly what's happening there. There's a video by like OK Go, or what's the band that does the free falling? We talked about
I think it's them.
Okay,
Yeah,
go?
I think we talked about that.
Yeah, there's a music video, like a band that does everything, they're like floating. They actually do exactly that. They get in a plane, they take the plane, they slowly cruise to a certain height, and then they drop at the rate of 9.8. And everybody starts to float, and they're recording the video while floating. And they only got like 20 seconds at a time, and then they have to come out of the nosedive, go back up, and then drop again. And it takes them like a couple minutes to rise up, and only have 20 seconds to fall. And the pilot has to keep doing these nosedives over and over. That's how they record the video. It's really cool.
So stressful.
Say again? Absolutely dangerous, but the pilot's trained to do it. But it's not just a random person.
Ever do that?
Well, don't forget, so what happens is this. When they're about to pull out of the nosedive, they have an alarm go off and everybody straps in. They're near enough to something that they can pull a strap to them and strap in, and then once they're there, they start going up, they're strapped in. And then once they start to free fall, they feel it, they take the straps off and start floating, and then they record the video. But it was like over and over they had to do it because of the fact that they were just iterations of it. So here's a methodology I want you to consider, when solving all force problems of this chapter. And we're going to use this in coming chapters as well. So first, I recommend drawing a sketch. A sketch is different than a free body diagram. A sketch is a sketch of the whole scenario. Second, well, and if the scenario has multiple instances, like time 1, time 2, time 3, several things are happening, maybe several sketches along the way. 2, draw a free body diagram. I'm telling you now that you will never get full credit on a math problem on the test if you don't have a free body diagram. On the AP exam, you get credit for a free body diagram. It's the part 1 of any force problem will be draw a free body diagram of all the forces acting on the bullet, all the forces acting on the car, on the person, on the roller coaster car. Whatever it is you're analyzing, drawing all the forces acting on it. So step 2 is the most important step of all. It's the most important step. Now, you then want to look at all of the forces acting at angles. If a force acts at an angle, you want to break it into its components, like we did with velocity. So when VO was like this, we said, oh, VOX is VO cosine theta, and VOY is VO sine theta. Remember, we broke into components? So if I have an applied force at an angle, what does that really mean? It means that I'm pulling it to the right and I'm pulling up at the same time. So step number 3 is to break up any forces acting at an angle into its components, Fx and Fy, we're going to call them forces. Step 4. Step 4 is the part that gives you all of the math that you're going to use. Step 4 is this. Use Newton's second law. Always. Write that in big letters if you need to. Always. You're always going to apply F equals ma. Now, we're specifically going to apply it in the x direction and in the y direction. And we're going to do that separately, and there might be some overlap. But we're specifically going to apply F equals ma in as many directions as possible for a given problem. Now, if I looked at the pencil case again, right? I put the pencil case down on the desk. What forces did we say act on the pencil case right now? Gravity, which is the weight of the object.
The table is the force going up.
Good. And then table pushing back up. Are there any horizontal forces acting on this right now at all? Nothing's pushing left to right. So if I were to draw a free body diagram, it would only have arrows up and down, right? So when I use Newton's second law, would it be in the x direction there? No. It would be in the y. So Newton's second law is specific to each direction. It's a vector quantity. The direction absolutely matters. So when we write F equals ma, we're going to one time look in the x, and at another moment we're going to look in the y direction. Yes?
What if an object was just sitting there and there was a wall like directly on the side of it, but it's not really like this, like that?
Still only vertical forces. Remember, the only time you're going to exhibit a horizontal force is if there's some external force pushing it, or if it's on an incline. And we're going to get to inclines soon too. Inclines are a whole other question, a whole other ballgame. But inclines do have many different types of force, and we'll get to those. That would be the only other time. Yeah.
What if you you had your iPad propped up against something and is the wall exhibiting force on?
Oh, then it is for sure, absolutely. Because without the wall, what would it do?
Fall.
Fall. Well, would that fall without a wall next to it? No. So that's what I'm getting at.
Okay.
You know? If it's actually supporting you, then it would be a horizontal force pushing back. Like it was not supporting that when I placed it here. Okay? Technically, the ledge is slightly this way, so the markers don't fall off. So technically, you could say the wall is supporting it. But if I just move the eraser out a little bit towards you, now it's not in contact. The wall is still there. Okay? All right. And then finally, the last step, which is step 5, is to solve the equation that results from F equals ma. And we'll get to that in a moment so we can see that happening. Okay? So let's discuss this term. This term is called normal force. We already got into it, but I want to make sure that it's clear. So a normal force is a reaction force. It's a reaction. And it's always acting perpendicular to the surface. It's a surface force that acts perpendicular to it. So the pencil case has the normal force pushing back up on it. If I were to look at this inclined plane right here, and this object resting on it, when the object is at an angle, it's still on a surface, right? And since we said that the normal force is perpendicular to the surface, the normal force here is at an angle also. If I do this, then the normal force moves. Look at the normal force. It's literally changing. My hand is the vector showing the direction of the normal force. It's always perpendicular to the surface. So when the surface is flat, the normal force acts in the y direction, straight up. But when the surface is angled, the normal force acts at an angle. We'll get to inclined planes with that concept. Third example of normal force here. Third example. How is it possible for me, a mere weakling, to hold, really, I'm not a strong person, really, to be honest. So, how is it physically possible for me to hold this eraser here? Seems pretty easy because the eraser's not an acid, right? How is it possible?
The wall.
Wall's definitely doing something. Good idea. Jack?
The small force from your finger is pushing into the wall, and the force is kind of spread out. So, is that part of it, or no?
Good idea, though. I like you're getting at. You're like, hey, there's more grip. It's a bigger surface, right? That definitely affects things for sure. The bigger surface. That's not what's happening, though. What's preventing it? Like, okay, take a bigger object now, right? I mean, oh man, I don't want to screw anybody's things up. Here, can I use your backpack?
Yeah.
All right. I'm trying not to get dirty. All right. So we've got M's backpack here, right? And I'm holding it against the wall. Notice how much harder I have to apply force here? Can I do the same thing as the eraser? I can't, right? I literally can't. But if I push hard enough, and kind of at an angle it looks like, but I can do it horizontally, her backpack gets held to the wall. Why is that? Why is that? Think about it logically. What's keeping it there, George?
Maybe because the wall's pushing back on the bag, and like those two forces against each other are like keeping it in place.
So George is on the right track that the wall pushes back. So these two forces are balanced this way, George. But why isn't it falling down, George? Why isn't it falling down? Because remember, pushing this way doesn't affect down. It only affects left and right. Why is it falling down, Vin? The friction between the object and the wall. Well, it turns out that when you push against the wall pushes back. And that's called the normal force also. So this normal force pushing off the wall. And the greater the normal force, the more friction you're going to have. We're going to get to that concept of more normal force causes more friction in the next section. But think about this. If I push the wall has to push back. So when I push on this object, sure, the weight acts down, right? The weight pulls it down. But the normal force now is no longer pushing back up because it's not sitting on a surface. If I did this, now the normal force pushes back up. But there is no surface below pushing back up. The normal force comes out of the wall or is directed away from the wall. Okay? The normal force does not act up in this scenario. It acts horizontally out of the wall.
So is that scenario kind of like the static friction, but just like sideways?
It's static friction, and the friction acts upward. It's balancing gravity, which is pulling down.
Yeah.
It's just sideways. It's all rotated 90 degrees. Yep. So what I want to point out is that the normal force is a reaction from a surface that is always perpendicular to that surface. Normal means perpendicular, by the way. In math, later on, you're going to hear the word normal, and it physically means perpendicular. Good.
So is there always like a force acting on each side of the object or not necessarily?
Unless the object is in outer space and it's having nothing next to it, not touching anything, then yes, there'd always be something acting on it.
Like up, down, and horizontal?
No, not always both, but there's always some force acting on an object. There's got to be, yeah. Okay? All right, let's take a look at an example of this. Okay, let's look at an example of this. So, the first example says the following. If an object is at rest on a table, so we're looking at the pencil case right now. It's at rest. The mass of the pencil case or the object is 10 kilos, and you're trying to lift it with an upward force of 35 newtons. You're applying an upward force. Will it lift off the table? If not, what is the normal force from the table? So let's start this problem first with a diagram. A diagram is always nice. Before we even get to the free body diagram, I could start with a regular diagram if I want to draw a sketch. The sketch for this one is not that detailed. There it is. I mean, this is pretty much the sketch right here with some external force acting on it. Again, this is not my free body diagram. Okay, this is just a sketch of the scenario. That's it. That's all it is. And the question is, will it lift off the table? That's what we're trying to figure out. So now what I do is I draw a free body diagram of the object itself. What pulls all objects down? Gravity. So let's draw this as F sub G. Remember, the subscript is G. It's not a variable right now. It's a subscript. It's not like I'm taking F and multiplying it by 9.8. That is not what I'm doing here. This is a variable with a subscript. All of my forces are going to have subscripts. Every one of them will have a subscript. If they don't, it's usually just some external force applied. But even that, I usually put FP for a push or a pull. Now, we know that if this object is resting on a table, then the table must be pushing back against it. And the table pushes back against the object with what we call the normal force. So this is the current situation before I try to lift it. So right now, before I walk over to the pencil case, this is the scenario. Then as soon as I get here and I try to lift upward with a force, maybe it's not enough force to lift it off the ground. I mean, you've done that before. Have you ever gone to the gym? Well, I mean, maybe you've done it before, I don't know. But if you've gone to the gym and tried to lift like a really heavy dumbbell and you just can't lift it off the ground, if you have like a 100-pound dumbbell on the ground and you physically can't lift it, you can pull as hard as you want. It's not going to go anywhere. You might lift with 80 pounds, but it weighs 100, so it's not going to move. If you lift with 90 pounds, you're getting closer, but it's still not going to move, right? You have to apply at least 100 pounds in order to overcome the weight pulling down. So the applied force in this situation is also upward, and the way I like to draw those is with the second arrow. Okay, the second arrow is in the same exact direction. I stack my arrows. Some textbooks put them next to each other. I don't like doing that because by putting them next to each other, sometimes they look like they're going away at angles. But these are both vertical forces. You follow what I'm saying? Sometimes textbooks will put both forces acting upward parallel to each other. But when I draw a diagram, it's really tough to draw that. To draw two perfectly parallel vectors coming from this little dot. So I like to stack them. Either way is acceptable. So if you prefer the other way, that's fine as well. So these are the three forces acting though. So that's the question we're having here. Is 35 newtons enough for liftoff to happen? Is it enough for liftoff? What do you think?
Yeah.
You think so? Why?
Because 35, I think 35 newtons is equal to more than 10 kilograms.
That's a good question, actually. Well, we should be able to figure it out, shouldn't we?
Yeah.
Because we are given the mass, not the weight. We are given the mass. M in this problem is 10 kilograms. The applied force is given as 35 newtons. Gravity is 9.8 meters per second squared. So this is my arrangement right here. These are all of the given pieces of information. So I need to start by looking and asking myself, okay, what are all the forces acting? And to do this, I'm going to do it very slowly for the first problem. And then I'm going to pick up pace from problems going forward. So for this first problem, I start with Newton's second law. The sum of the forces in the y direction equal MAY. So that's my starting point right there. This symbol again means sum. The sum of. So what forces are acting positively in this problem? What forces are acting positively, Julia?
Normal force and push.
Pull, push, either one. Good. I would say pull. Pull that one. So those are both positive forces. I agree. And then there's one force acting negatively here. What do we call that force? Good. The force due to gravity. So I put a negative sign there. So this is my equation for Newton's second law. So for all problems this year in forces, we're going to start with F equals ma, always. Always starting with F equals ma. And then we're going to replace this with literally all the forces acting. Anything acting up or in the positive, we'll call positive. Anything acting down or in the negative, we'll call negative. So we don't need to label G as negative 9.8 anymore. Do you remember last chapter? With projectile motion, this was always negative 9.8. Think about it logically. This already has a negative sign, doesn't it, right here? So when I replace FG with its formula, what was the formula for FG a slide ago? Or 2 slides ago, what was the formula for FG? FG is simply?
FG equals mg.
Equals mg. So when I replace that with the formula mg, the equation becomes this. That's the equation now. I'm only replacing FG with mg. And look, the negative sign is already there. So don't double negative by accident. So in this chapter, and going forward, G is going to be 9.81. It's only with projectile motion that we need the negative sign for G. For all other topics this year, we're going to see G being positive 9.81, which is why on your formula sheet it's not listed as negative. It's listed as positive 9.81 actually, or positive 9.8. But in projectile motion, we need to know that it decelerates you. It pulls you down, which is why it's a negative quantity. It's pulling you down to the ground. Good.
Why did you replace it with energy?
Because that's the formula for it. If you go back a couple slides, we wrote down that the weight of an object is equal to the mass of the object times the gravitational constant on Earth. So this replaces Fg. Just literally swipe up 2 slides. It's a formula. It's nothing more than that. It's just replacing the formula given. And we're going to have a couple of mini formulas in this chapter that are going to replace specific types of forces, and this is one of them. This formula is going to become pretty much second nature to you. When you're asked to find the weight of an object, mg, automatically, mg. Some teachers actually, and you can do this if you want, some teachers don't label this as fg, they just label it mg. And you can do that if you'd like, that's fine with me. If you remember better, say, call the weight mg every time. I write it as fg because I like to think of this as a force due to gravity, and then I remember that fg is just mg. And I actually think that this is on your formula sheet. I think this formula here, it might be, I think it is actually on your formula sheet. If it's not, it's okay, you'll memorize it, I promise. Now, the problem is still not over because we still don't know what the answer is. It says, will it lift off the table, right? Will it lift off? Let's ask this question now. If I lift this off the table, follow me please, what's the normal force then? What's the normal force, Nora?
0.
0. Why, Nora?
Because it's not touching the table and you know it's not exerting force down on the table.
Yeah, it's not exerting a force on the table. So can the table exert a force against it? Physically can't. There's no contact. It's a contact force. The normal force is always a contact force and not a distance force. So if it's not on the table, there can't be a normal force. So the question really becomes this. If I can lift it off the table, then this drops off. You with me right now? If I can lift it off. But if I cannot, I gotta use your thing again, sorry, I'm gonna zip it. If I cannot, but I apply, let's say that the weight of this object is 2 pounds, US pounds, okay, 2 pounds. And if I were to apply a force of a half a pound, can't get it. A pound, I still can't get it. But when I reach 2 pounds, it just starts to come off the table, right? So if I apply a pound and a half, how much does the table have left to cover?
0.5.
Only half a pound. Again, think about this for a second. This weighs 2 pounds, this weighs 2 pounds, and I lift with a pound and a half. How much is left for the table to resist is only a half a pound. Make it easier. Call it 5 pounds. If I lift with 4 and it doesn't lift off, what's left for the table? Only 1 pound is left behind. So really, if I don't lift it off the table, we'll still have normal force. So we'll have to calculate Fn and read the problem. It says, will it lift off the table? Will it lift off the table? If not, if it doesn't lift off the table, what is the normal force? And that's the scenario that we're probably going to be in, where I try to lift it, but it's not enough strength. So how will I be able to tell if my lift force up will overcome the weight of the object pulling down? How can I figure it out? Physically, how can I figure it out? I don't know.
By like trying to pick it up.
Okay, physically by trying to pick it up, yeah. If it's a real life scenario, by trying to pick it up. In this problem, though, how would I numerically determine if my applied force exceeds the weight of the object?
You would see if the left side is greater than the right side.
You're on the right track. I get what you're saying, George, but not exactly. You're on the right track, though. Again, listen to my words. Ready? How can I figure out if my applied force exceeds gravity, exceeds the weight of the object? Good.
Just greater than if the applied force is greater than the gravity.
Yeah, so look, don't we have the applied force? So what should we probably calculate in this problem before we even do anything? The weight of the object. If this number is more than Fg, it's definitely going to lift off. And now the problem doesn't have normal force anymore because I've lifted it off the table. Let's calculate Fg on the side over here. Fg is mass times gravity, which is 10 times 9.8. So the weight of this object is 98 newtons. Give me another minute of your time, please. The weight of the object is 98 newtons. But what was my applied force? Only 35. I am weak. I am not strong enough to lift this off the ground. I only applied 35 newtons, and yet it weighs 98. So is it going to move off the table? If I'm not applying enough force, will it move? So what's going to happen to the acceleration of this object? What would the acceleration be if it's not moving? That would be 0. So based on this statement, take a look. Because it's not moving, this goes to 0. Again, because it's not moving, MAY is really 0. It's not lifting off. But, if it were lifting off, then, let's take a look again, take a look up here, then this would be 0. If it does lift off the table, then the table can't provide a normal force anymore, so this cannot be here. And if it does lift off the table, what's the only way you can gain velocity? By having acceleration. So it turns out that if it did lift off the table, this would not be 0, and we would have to calculate acceleration. But if it doesn't lift off the table, then it is 0, and now we have to calculate the normal force. So let's solve for Fn. Let's solve for Fn. Fn will equal, I'm going to add mg over, I'm going to subtract fp over. That'll be mg minus fp. And that's exactly what you guys gave me as an answer before. When I said, hey, this pencil case weighs 5 pounds, and I lift up with 4, what's left of the table? You all said 1, right? How'd you get the answer? You subtracted the 2? Look, it's exactly that. How much does it weigh? 98. That goes in right here. How much do you pull up with? 35. That goes in right here. So it weighs 98. You pull up with 35. Not enough to lift it. Therefore, there's got to be some normal force left, which is what's left over. So my normal force would be the weight of the object minus the applied force I give it, which in this case is 63 newtons. Now, I want you, listen carefully, I want you to look at, hold on. Yeah, okay. I want you to look at we're going to do example 3 together. I want you to look at example 4. Okay, I want you to look at example 4. You had homework due today, 4.1 to 4.5?
Yeah.
Make sure that's in, obviously. If it were me, until Thursday, I'd probably start the problem set for 4 and 4.5 or work on my project a little bit. But I want you to do example 4 in the notes. And it's very similar, but what do you think is going to happen in example 4? Yeah, this applied force will exceed the weight, and therefore it will lift off the table and will have acceleration. This will not be 0. Instead, this will be 0 if it lifts off the table. Okay? All right, guys, go. Have a good day. Thank you. Example 3 says, a small object is stacked on top of a larger object, and they are both on top of a table. If the masses are 5 kilograms and 15 kilograms, what is the normal force acting on the object? Now, in these problems, when they say small object and larger object, the assumption has to be that we're referring to its mass and not its volume. Is that clear? Okay, because I understand, trust me, like this box here could be a really big object, but if there's nothing in it, the mass is very light, right? And this could be a very small object, but this could be heavier than this entire box if this box were empty. So in physics problems, when they talk about large and small objects, and you're talking about forces and mass, they're referring to the mass. So 5 is the smaller object and 15 is the larger. Is that clear what's happening here? Okay, it's not about volume, we're referring to mass. Regina, sorry, you got a hand up.
I was gonna say, for the one before, I did a different way and I got the same answer.
Can you tell me?
I don't know what I did. So I found the force, I did mass times, I found force was 100 and the mass I put in 8, got 12.5, and then I subtracted gravity to get 2.69.
Subtracted gravity. You subtracted 9.81?
Yeah.
No, you just got lucky then that it worked, so yeah. Gravity has to always be multiplied by the value of m to give you the weight. I could look at your work later and see, Regina, just to see why it worked out. And you're saying you got exactly the same answer, like,
2.69.
and that's what we had, 2.69?
0.7.
Yeah, so it's possible it just happened to happen that way, or maybe there's something you did that made it work. I can look at that separately, yeah, I'm happy to. So we've got these two objects stacked, 5 kilos and 15 kilos. Now, I'm not going to really push on the quiz much about this, but going forward, it needs to be done the right way. You can't label three-body diagrams in the whole diagram. Okay? Some of you did on the quiz. I'm not going to take off right now. Okay? I walked as I was going around, but I wasn't going to say anything. You want to draw them separately. Always draw them separately. A free body diagram is all the forces acting on a single object. So because we have two objects here, like you did on the quiz, you draw two separate points. This is object 1, this is object 2. Okay, we draw them physically separately so the vectors don't overlap. Now, object, let's say this is small and this is large. We'll go small here and large here. And I would personally always denote which one I'm labeling so I know which forces are acting on which object. So small and large. The small is on top. What is acting on that small object on top? What's physically acting on it? Give me something. Gravity. So the weight of the object is absolutely acting on it. So let's call that FG1. Call it FGS for small and FGL for large. Or A and B is fine, or 1 and 2 is fine. Whatever subscript you choose, just be consistent throughout the problem. If you call it A and B or 1 and 2, it doesn't matter. Large, small, Joe, Chris, it makes no difference if you call these names of objects, but be consistent, that's all. Jack.
Another force is coming from the box underneath and I guess the table as well, going upwards.
But what's actually acting on the small object? Is the table actually touching and acting on it?
No, it's the
So what is it
box.
then? Just the box below. So let's listen to what Jack just said there. So there's a normal force acting on this object from the object beneath it. The table only acts on the big object. The table pushes on the big object, but the big object pushes up on the small object. So Fn1, I'm calling it 1 right now. Why do you think I'm using 1? Because there's going to be 2. That's the only time I denote 1 or 2 or A or B is if there are multiple parts. So the bigger box supports the smaller box with a normal force coming from the bigger box. So for example, literally look over here. This object is currently supported by the table, right? When I place this box on top, sure, the table is now supporting both of them, and I get that. But the table is only physically supporting this one right now, which this one in turn supports this one. If the top of this box was not structurally sound, what would happen is this would literally fall through the upper box or break through it. Now, the table might stop it, it breaks through and falls to the bottom, and then the table stops it, right? But the upper box is what's physically supporting the lower box is what's physically supporting the upper box here. That's what Fn1 is. Fn1 is the reaction from the larger box pushing up on the smaller one. You got a hand up.
Will there ever be a time where there won't be I'm confused on normal force.
So normal force always exists when you have an object against a surface. So if I push against the wall, if a roller coaster is going through a loop-de-loop, when your body gets sucked to the seat, when this pencil case sits on the table. So in all of these scenarios where it's resting on a surface, there's going to be some form of normal force. Now, could that normal force eventually be 0? Sure, and we saw that in the other example, if you pull up on it with enough force. Or the roller coaster problem. There's a type of that problem where there's an instant where you feel weightless for a moment, and we'll get to where that is. So the normal force is a little bit confusing, but for now, I want you to think when it's on or against the surface, normal force reacts from that surface. Okay, so what is the surface that the small object rests on? It's the large object. What is the surface the large object rests on? It's the table, or whatever it says here. Okay?
Another question. When you draw your arrows, does it matter if it's like shorter or longer?
So that's a great question. You know, I've never cared about the vector length. But Mr. Donachek the other day said to me that you probably should indicate which is larger or smaller with the length. The problem is, I don't know Fn1 right now. I don't know the value of it. So I can't logically illustrate this. But on an AP exam, if you're told the upward force is 200, the downward force is 20, you should respectively make the upward force longer if you know the values. But I don't know the values, so for here it doesn't matter. But if you do know them, it is understood on an AP exam that you should draw them proportional to the number given. Okay, it's not going to be perfect, obviously. You don't have a rule or anything like that, but generally speaking, okay? Good question. Lower mass. What's acting on the lower mass? What do we got? More, give me something.
G,
FG1?
yeah,
Why?
because it's gravity.
So what is FG1 in your mind again?
It's still the gravitational force
Of?
of the larger body.
So we can call that FG1, even though we called the other one FG1?
I guess two.
Yeah, I guess 2, right? So I had to stop more there because you can't call the other one FG1 if we're calling that one FG1. Now, here's the thing, Justin.
Doesn't the 5 kilogram also put?
The upper mass, Vinny was seeing it too, the upper mass also pushes down on the lower mass. So it turns out that it's not just FG2. FG2 is the weight of this object pulling down on the table surface, or on itself really. But the upper mass also pushes down on the lower mass. So it turns out, and that's why I was giving you that kind of weird question there, it turns out that FG1 also acts on this mass. Think about it. Really think about it for a second. If your hand is here and you put an object on it, what's acting on your hand? The weight of this object. Think about the dumbbell situation in the gym we talked about. If you literally are able to lift a dumbbell, you must be able to lift up with a force equal to the weight of that dumbbell. If this is a dumbbell that weighs 5 pounds, I need to lift up with 5 pounds. It's not going to work if you can't. So this problem here of the 5 kilogram on top of the 15, the 5 kilogram pushes down on the 15. Think about it. If you ever unroll a poster, who likes to put posters in their room? It's a big thing I did when I was younger. All right. So posters aren't a good example. So that was going to be an easy one. What?
I feel like soccer jerseys.
All right, on your wall you put a soccer jersey. All right, so let's hypothetically say, oh great, okay, this is perfect. Soccer jersey, right? Your soccer jersey's all wrinkled. You can't put that up on the wall if it's wrinkled. That looks terrible. So what do you have to do? And when you iron, what do? You apply a force downward on the shirt, correct? And that flattens the shirt. I was going to use a poster. When you get a poster, it's always rolled up in the tube, right? You know what I'm talking about? And when you want a poster to look nice on the wall, you lay it out. And when I was a kid, I always did this. I put textbooks on top of it. And you literally lay out all the textbooks on top of the poster and let it sit on a table for like 4 or 5 days, and it will flatten out, close to flatten out. Because what are you doing? You're applying a downward force on the poster with the textbooks. It's literally squishing it. That's what's happening here. The 5 kilogram mass is applying a downward force on the 15 kilogram mass. So therefore, we have a second force acting downward. Could we draw this force from the top acting down, pointing to this? Sure we could. I'm going to show you what I mean. I could draw this force like this instead. And some people like to do that to show that it's coming from the top of the object, pushing down on it. That's fine. I personally like to draw all my vectors on one side or the other. So I don't like the direction being different on the top. So any vectors I draw on the top, I like to draw upward. So that's why I put FG1 below it, but it shows that both are pulling down. Pulling down, I should say, and this one is pushing down. See the difference? The weight of the bottom object is pulling on it. The weight of the top object is pushing down on the bottom object. So this is a force of push coming down on it. This, though, gravity is physically pulling you down. Pull and push are very different, right? We know that? This is a push. This is a pull. Okay, very different things. George.
So when you're putting like your books on your poster, is the poster pushing back up on the books, or like the table under the?
That's a great question, George. The table is pushing the poster is pushing the books.
Okay.
But the table is enough to support both, which we're going to see now in this one. Okay? Yeah.
Is FG1 smaller than FG2 because we know the mass?
Absolutely, absolutely. So for that one, we can indicate the length of the vectors. You hear the question there? We know FG1 is definitely smaller than FG2, for sure. Because FG1 is the weight of the small object. Yep, absolutely. Even though we didn't calculate it yet, we know that for sure. Now, what is holding both of these objects up? Both of them, Natalia?
The table, so we FN2.
Very good, Natalia. Oh, the table, which is FN2. Oops, I did not mean to use red, sorry. The table, which is FN2. Now, could you tell me something else? Which is going to be bigger, FN2 or FN1? Which is going to be bigger? We're not doing any math. Which is bigger, Jack?
FN2.
Why?
Because it's holding more weight.
It's holding both, more weight. So FN2 vector could be drawn bigger than FN1 if you want to be precise with your vector length, okay? But we know already that Fn2 is going to support both. Now, in this problem, is anything moving? Any motion at all? No, right? So if there's no motion in the problem, and we're talking about an object that's on a surface resting, what can we assume for this problem?
No FP.
No what?
No FP.
Good. No applied force. What
No
else?
acceleration.
And no acceleration. There's no applied force here, which is why it's not accelerating upward, no FP, but there's no acceleration because we know that these objects are at rest. So when I write my equation of motion, I write F net equals MA, and it's M1 first. So we only look at the first object, and we only look at its free body diagram first. It's the first time you're seeing multiple objects, if I'm going through it slowly. So you only look at the first objects first, which means that this F net is Fn1 acting up, and that's coming from right here, and then minus Fg1, which is pulling down on it. And that's going to equal 0, because again, there's no acceleration for the first or the smaller object. Remember, it's got a normal force pushing up on it from the bigger object. It's got its weight pulling down. Normal force is positive, weight is negative. Up versus down. Positive versus negative. So from this, we can find the normal force, right? Because we know Fg1. Fg1 is calculable. I don't know if that's the right word. You can calculate Fg1. And that's the formula for Fg. Right? Fg equals mg. That one, again, I said it last class, I'll say it again. You will memorize that. I'm telling you now, I guarantee you 100%, you will memorize that Fg equals mg. If not, I can't recall, maybe I'll check actually while we're here. Is it on your formula sheet? It is not. It is not on your formula sheet for the AP exam. So you know what? You will definitely memorize it. Okay? Fg is always mg. I'm putting a 1 here because I'm talking about the mass of the first object. So Fn1 is simply equal to m1g. And that makes sense logically. Here's how I would read this. If you want to write this in words and you're not understanding it or seeing it right away, I would recommend that. Here's what I'm seeing. Fn1, aka the force upward from the bigger box, is equal to m1g, aka the weight of the upper box. So the bigger box, which is the bigger cardboard box here, its normal force pushing up is only balancing the weight of this object, right there. This object's weight pushing down is balanced by the normal force pushing up. And that's what the statement says. That's why it's important that we look at variables also, not just plugging numbers. This literally says the force pushing up from the big box equals the weight of the small box. That's what that statement says right there. Now we plug in numbers. 5 times 9.8, 40 something, right? 49. Fn1 is 49 newtons. Okay, 5 times 9.8 is what that number is. Because M1 was 5, smaller object. How about M2? Can somebody give me the equation for M2? The upper mass, or sorry, the heavier mass, I should say. Not the upper one, the heavier one. Jack, go ahead, take a stab at it.
Not exactly sure.
It's okay.
M2, you would write down Fn2 equals M2 G.
Close, Jack. Give me the, before you solve it, I want the governing equation from the very beginning. Like, I know that this is true right away, right?
Yeah.
I start with this always. So start with that and now fill in the blanks.
Okay, so Fn2 minus F1 plus Fg1 plus Fg2.
And I'm going to write it like this. I like what you're saying. That's fine. Keep going.
Okay, equals M2A.
Which is?
0.
Okay, very good, Jack. So Jack did something which is fine. He said Fn2 minus the sum of these, which you can do. But then you would just distribute the negative anyway, wouldn't you?
Yeah.
So I'm just going to write them both as negative because they're both acting down. I like to just look at diagrams. I stare at my free body diagram and I say, what's up? What's up? What's up is Fn2, so that's positive. What's down are these two, so those two are both negative. Okay, and I always do this way. I just literally list what I see in my free body diagram. Now, what is known? These values are both known. We know the weight of both objects. And if I were to solve this, right, this is what it looks like next. I'm just replacing FG with its formula. And then I'm solving for Fn2. Can somebody make a statement in their own words that illustrates this last line of the equation? What could that statement be, Christina?
The normal force on the other object is equal to or balanced with the weight of gravity pushing down the object.
Good. Both, good. So the normal force acting up from the table, let's say, because we know that that's what this is equal to the weight of both objects. And that is logical. Look at the boxes. They're not falling right now. Why not? Because the countertop supports both of their weights, really. And that's what the statement says in the end. The countertop, Fn2, is equal to the weight of both of these objects, or the force provided by that countertop. And that's what we see in this equation. So this number will clearly be greater. Okay, M1G we know is already 49. And then if we add FG or M2G, we get 49 and 147, right? Yeah, 49 and 147, totaling 196. Okay, 196. And that's logical that that answer was greater. We saw that happening already, that this value would be greater than this value because it supports multiple objects. Multiple objects. General questions or specific questions on this example I'm talking about. This is the first multi-mass system we've really looked at, right? When we do that, the key, if you want to write it down, is to draw both free body diagrams separately. That is the key to this problem. Draw them separately, analyze them separately. There may come a time where we develop what's called a system of equations. We've done that already. And we had, if you remember from projectile motion, our linking variable is time and initial velocity and the initial angle. Those are the three things that carry over in both the x and y direction. It's going to happen here also. Think about the quiz problem you had today. Remember the one with the rope? That rope, we're going to get into tension soon. Okay, we're going to talk about that a little bit. But that rope that's acting over that pulley system right there in that problem, that rope is applied to both of those masses. So that's the variable that can go in both equations, Ft in that problem. Okay, we're going to see that more in a little bit. I asked you at home to look at, how does this problem differ from the one that we ended class with? Because it looks very, very similar, right? Jack, what do you think?
So since Fp is greater than Fp, the box is lifted up, so Fn equals 0.
Very good. That is the statement. Very good. Well stated, Jack. Fp, the applied force upward in this problem, is 100 newtons. It turns out that the weight is only, 8 times 9.8, 78.4 newtons. That's the weight acting down on this object. So clearly, if the applied force upward is more than the weight of the pencil case, it will lift off the table. And when it lifts off the table, there is no longer a normal force in the problem. Okay, therefore, Fn equals 0. And we can follow up by saying, therefore, the acceleration does not equal 0. These are the keys to this problem. Because the vertical force applied is greater than gravity, it must accelerate. Why must it accelerate? Why must it accelerate? I just said because the force upward is greater than gravity, but why must it physically accelerate?
Because it's angular velocity is 0.
Yes, the current velocity is 0. The current velocity is 0. If I literally move it at all, I'm giving it velocity, aren't I? And to go from 0 velocity to some other velocity, you must have acceleration. That's the kinematic answer to that question. The dynamic answer, forces, is simply, hey, the forces aren't balanced, right? If the forces aren't balanced, there must be an acceleration. So if the upward force is more than the downward force, it must accelerate upward. What if the downward force is more than the upward force?
Could be negative acceleration.
Yeah, which is this, right? downward force is gravity. As soon as I let go, the only upward force acting on it is air resistance, which is negligible. It's pretty much nothing in this problem. It's not a lot at all. So the downward force exceeds the upward force of air resistance, and therefore it accelerates downward. So either way, if there's an imbalance of forces, there must be acceleration. So for this problem, my free body diagram is FP upward, FG downward, and then we had Fn, which we eventually realized that went to 0. But with the free body diagram, I would probably start by drawing Fn in the diagram anyway, because we don't know if Fn exists in the beginning of this problem. Once we recognize that Fp is more than Fg and it lifts off the table, then we can cross off Fn. But in the free body diagram, you still want to include it because it's like one of those, ooh, that could be a force there. And that's going to happen a lot with Fn. Where you start by drawing it in your free body diagram, and then you may not have an Fn value. It may become 0.
Does it matter if you put the force to pull above or below?
Doesn't matter, no. Yeah, either way. As long as the vectors are both collinear, or both acting upward in that case, you're fine. Okay? Now, what does my equation become as a result? I literally use sum of the forces equals ma. Right? F net equals ma. What's acting up is Fp. What's acting down is Fg. So again, and I'll put a little y symbol because it's in the y direction. But there's no x going on at all in this problem. There's no horizontal force, nor is there horizontal motion. So although I'm writing F net in the y direction equals may, I don't need the y as much in this problem. But in a moment, we're going to look at problems that involve both x and y directions. So we're going to have to specify which direction we're looking at. Here, though, I'm only looking vertically. Anything acting up is positive, anything acting down is negative. Now, there's going to come a time where I'm going to switch those things. Where I'm going to say down is now positive and up is now negative. Okay, so get that in your head already. I'm not going to do it yet. We're going to do it in a few problems from now. Where down is going to be considered positive, or I'm just going to change it up a little bit so you can think differently, especially when we have systems that are connected with ropes over pulleys. Because when this one moves down, this one moves up. Imagine a pulley system, just so you're aware of what I'm saying. Imagine a pulley system like this with an object on each end. If one object is heavier than the other, it will move. We assume no friction right now. We'll get to friction later. But if they're the same weight, they're going to be balanced. They're going to stay. And they'd actually be level if they're the same weight. But if one of these is greater than the other in weight, it's got to rotate. So already, if this one rotates down, this one rotates up. If this one rotates down, this one rotates up. So the motion is either clockwise or counterclockwise. So in those problems, we might start looking at our up and down in different directions. And we'll get to that when we get there. Okay, not involved for this problem, really. So the final answer here is just going to be that AY equals FP minus FG all over M. And our goal is to find the acceleration, right? We're looking here. It says, if so, if it does lift off the table, with what acceleration? We don't have to worry about the second part, right? We don't have to worry about that part. If not, what is the normal force? Because it does move off the table, so normal force is 0 for sure. So we're answering what's highlighted in red. What does A become as an answer for this? What does A become? Jack, go ahead.
2.7.
Good. Thank you, Jack. 2.7. Okay? 2.7 meters per second squared. And you're going to notice more and more that I'm not going to do the tedious math in front of you. I'm going to allow you to recognize what you need to do. This is 100 minus 78.4, all divided by the mass. Mass is 8. Okay, all divided by 8. So our answer validates our statement. Acceleration is positive because the upward force exceeds the downward force. The answer validates our statement from earlier. Okay, so let's go back now, and let's go back to look at example 3. Let's look at example 5. This is where the bonus comes into play. I said I was going to give you guys an extra credit. This is the first extra credit opportunity of the year, actually. And the way I do extra credit is if you do it, you either get a 1, a 2, or a 3. Well, 1 means you did it, but really didn't do it that well. But I give you some points for doing it. A 2 means you did it, but the explanation is like, eh. A 3 means you did it, and your explanation is really good. And 1, 2, or 3 are the amount of points that give us a bonus and goes on your test. So if you want to do the bonus for this, I'll explain in a moment what you can do. Okay? We'll do the problem first, then we'll talk about the bonus. A person rides an elevator. Well, it's rare that I get bonuses, by the way. It's like 2 or 3 times all year. Person rides an elevator while standing on a spring scale. If you don't know what a spring scale is, well, first, if you don't know what a spring scale is or an analog scale, you're all probably used to digital scales. What's an analog scale or a spring scale?
Well, I'm just assuming it's like a step on a scale and measures like the tension and then like converts that to a weight.
Very good, Jack. Well explained. Do you know what it looks like physically? Have you ever seen it before? What a spring scale, how the reader would look on that?
It looks like a dial.
Yeah, very good. It's like a dial. Okay, so if you think about these old scales, the new ones that are digital, they work with a little electric sensor. It also senses the compression. It takes that little electrical signal, converts it to a value, and you get your weight. But an analog scale, you would literally have a little dial, right? It would go like this. Right? It's like when you measure voltage on the old voltmeters. Voltage coming out of the wall literally spikes. Or those like sound meters you have at like basketball games where they show the sound going up, it's measuring decibel levels. This is an analog scale. So as you step on the scale, it does this, right? It goes, and it rests at where your weight is. Now, if somebody else suddenly stepped on the scale, it would go up. If you partially stepped off the scale with 1 foot, it would go down. So if you use an analog scale on an elevator, you can see a fluctuation in weight based on the motion of the elevator. And we're going to talk about it here, but your extra credit is going to be to do exactly this, to go on an elevator with an analog scale, which is going to be tough to get one, I know that. If you have a digital scale, it'll work, but sometimes it doesn't, because the digital scale, it waits for it to hone in on a value. Have you used a digital scale before? When you step on it, it like fluctuates until it finds your value, and then it blinks 3 times. Okay? So yeah, you're gonna have to be awkward as anything and be on your elevator with a scale, and you have to record it too for the extra credit. Yeah. So I'll get into it in a second. So, is she laughing or crying? Yeah. And when people come by, you gotta say, I'm doing a physics project. And they're like, no problem, no problem. Oh, then you gotta find an elevator somewhere. You can use an elevator anywhere, any elevator will work. I don't have the key, so if you want to go get the key, you can. I don't use that elevator. If you can get the key somewhere and somebody's willing to lend it to you and you want to do it, but I would recommend you do it somewhere privately, because then you also need to bring a scale in.
For the scale, is it like the really big one that's like heavy and stuff?
No, you can get one that's like, it's like the normal size of a normal scale, except it just has a dial on it. You can borrow it from a friend or family member. You can put someone else if you don't want to put your own weight. I don't care. Any object. It doesn't matter what the object is.
So, are we going to stand with the scale in the elevator?
Or somebody else can, and then you could record the reading. Well, the recording needs to have somebody or something on it so I can see it, and then the actual analog. And then you have to explain the answers. And it's a video submission, yeah. I'm going to get into it. Give me a second. I want to go over the problem. All right, let's get into this problem and we'll talk more. So here's the question. The question says the following. What does the elevator or the scale read if, in this case, there's acceleration upward? What does the scale read if there's acceleration upward? That's the main problem that's posed here. So we're told that the person's mass is 10, so let's start writing stuff down. The mass is 10 kilograms. The acceleration is upward, so I'm going to call that a positive. And you know g is 9.81 meters, or 9.8 meters per second squared. Those are the 3 things that we know. And we're going to attack the first problem first. Okay, we're going to attack this problem. What does the scale read if the person's mass is this and accelerating up? We'll get to the second problem in a moment. Okay. So here's the 3 givens: mass, acceleration, and g. If I were to look at this problem now, and I were to draw a free body diagram of the person, let's put a dot here. On the left, I'm going to draw a sketch first. Elevator, elevator cable, scale, person. Okay, here's my sketch. This is not my free body diagram, this is my sketch. Now, the elevator pulls up or down on the object or on the elevator cart, which in turn affects your body's motion. And you know this, whether you realize it or not. When you go on an elevator, there are moments where you feel kind of weightless. Not weightless, but you feel like you weigh less. And there are other times where your legs feel a lot of stress. Suddenly you're like, oh my gosh, all that force on my legs. And we're going to discuss why that is, and you're going to prove this in your extra credit. So mathematically here, I'm drawing a free body diagram of the person, okay, of the person. Not the scale, not the elevator, but the person. Now, what acts down is the person's weight, and that always acts down. Because the person is resting on a surface, what acts up also? What is it? Normal force, because it's acting, again, it's resting on a surface. And that's all it's acting on this. What provides Fn to the person? I want a direct answer, not an indirect answer. A direct answer. Justin. The scale. Very good. Not the elevator card. What provides Fn on the scale? The elevator card itself. The person puts weight on the scale. Weight on the scale. So remember, this is very similar to the problem we just did with two stacked objects, right? But we are really concerned with what the scale is going to read, which is very difficult because nowhere do we say we have a reading for the scale. But here is the thing. The way a scale works is it's literally showing you the normal force pushing back. So let's write down in big letters that the scale reading is the normal force. Again, the scale reading, and this is for all problems, I'm guaranteeing you 100% on an AP exam, there will be a problem involving a scale. It is on every single one. Okay, you will have it on my next test for sure. A scale reading tells you the normal force. So in this problem, it says, what does the scale read? So what are we really asking? What is the normal force? What is the normal force? Now, you might think, by looking at this, well, look, oh, Mr. Howell, we've got normal force up, we've got the weight down, they're balanced, so maybe just the normal force equals the weight. But that would assume that the net force equals 0. When does the net force equal 0? Only when, yeah, when you're at rest, when acceleration is 0, or you're at a constant velocity. Give me one more minute. In this problem, acceleration is upward. So here's what I'd like you to do. I'll give you the governing, and I want you to finish it. This is the governing right here. This is the next line. Okay, this is literally our equation. And our goal is to figure out Fn. So let's move Fg over. Let's figure out Fn. And then I want you to look at the second part of the problem. Okay, I'll get more into the extra credit, I guess, on Monday, unfortunately. Okay, maybe I can even write it up and send it to you if you want to do it with me. Okay, have a good weekend, guys. We'll see you all on Monday. Enjoy your field trip. I know you're meeting now, right? Yeah? Have a good time.